Hi and hello, this is Shashank from Aero Fortsum of roll number 2295182147. This is a Tech Talk video presentation for the topic for the subject aerodynamics. The topic I've chosen for the Tech Talk video presentation is compressor blade surfaces and its flow dynamics. Analyzing boundary layer flow dynamics on compressor blade surfaces. The boundary layer is a crucial factor in compressor blade performance. The What's a compressor blade? If we imagine a propulsion system of a or a turbojet engine of an aircraft, the compressor blades are the blades at the after the inlet, which are used to compress the airflow. And when the air flows through the compressor blades, it gets compressed or decrease. There is a decrease in volume, and there is a formation of boundary layer along the compressor blades, which is a crucial factor in determining the performance of compressor blade. Understanding its flow dynamics is very essential for optimizing efficiency and preventing stall. The compressor blades rotates through the axis of shaft or turbine. In turn, there is an airflow which might cause a boundary layer, and understanding the flow dynamics through the compressor blades is essential for optimizing the efficiency and preventing the stall. In this presentation, let's analyze the factors influencing the boundary layer behavior on compressor blade surfaces. Boundary layer formation. The boundary layer forms as air interacts with the compressor blade surfaces. This thin layer of slower moving air affects aerodynamic performances. When the air flows through the compressor blade, on the surface of the blade, there is a formation of boundary layer. A boundary layer is a layer which has zero velocity, zero velocity with respect to the surface of the surface of the compressor blade. The velocity of the airflow is negligible or relatively zero with the surface. This thin layer of the boundary layer, slow of slow moving air affects the aerodynamic performance. The thickness and the formation of the boundary layer also affects the aerodynamic performance of the aircraft. Understanding its formation is vital for optimizing blade design and performance. If we understand and go through how a boundary layer is formed on the surface, we can optimize the blade design. Also, use different kinds of materials for the designing, different shapes, different interactions to optimize the performance. Boundary layer thickness. Thickness of the boundary layer directly impacts drag and separation. Boundary layer is Boundary layer thickness is the distance between the surface and the velocity, or thick, thickness is the distance between the layer which is attached to the surface and the layer which is above the surface, which has velocity which is equal to the free stream velocity. And the thickness of the boundary layer directly impacts drag and separation between the flow and the surface. Factors such as blade geometry and airflow speed these both the factors influence the boundary layer thickness. If we consider a compressor blade with a and consider its blade geometry, it influences the boundary layer thickness. The geometry of the blade or the dimensions it has is how we determine the boundary layer and how does it form. If we go through those factors, we can we can understand the formation of boundary layer and also determine its thickness. Also, the airflow speed, the free stream velocity which is entering the propulsion system and the compressor blades, it also affects the boundary layer thickness. Understanding these both the factors is crucial for optimizing compressor blade efficiency. If we want to increase the efficiency of the compressor, we need to study the boundary layer and the formation and its thickness. And these blade geometry and airflow speeds are the factors which are influencing the thickness. So studying both these factors and optimizing them will eventually increase the efficiency of the compressor blades. Boundary layer transition. The transition of boundary layer from laminar to turbulent significantly impacts blade performance. The laminar and turbulent regions are basically determined by Reynolds number and surface roughness. When there is a when if we the transition from laminar to turbulent is short. If this transition is short, the efficiency then can be increased. Understanding these factors is essential for preventing flow separation. Impact of flow separations. Flow separation within the boundary layer leads to losses in efficiency and increased drag. When the flow due to the boundary layer formation is separated from the surface, which means it does not interact with the surface, the airflow cannot be compressed or there might be a turbulence or a disturbance in the flow, which leads to the losses in the efficiency of the compressor blades. And due to the turbulence or the disturbance formed in the airflow, it in turn increases the drag. Understanding the factors that contribute to flow separations is crucial for optimizing compressor blade performance and preventing stall. Such factors, the flow separation, thickness, turbulence, airflow, velocity, geometry, considering these all factors and optimizing them will lead to greater compressor blade performance, greater efficiency, and expected performance can be lead out. Boundary layer control. Effective boundary layer control is essential for optimizing compressor blade performance. If we there will be a formation of boundary layer on the surface, but if we have a control over it and preventing the increase in the thickness or the separation, we can optimize the compressor blade performance. The effective boundary layer control is essential for optimizing compressor blade performance. Techniques such as boundary layer suction and surface roughness manipulation can be employed to manage the boundary layer and prevent flow separations. Boundary layer suction and surface roughness manipulation. If we manipulate or optimize the surface and its roughness, we can actually get control over the boundary layer and prevent flow separation, which leads to turbulence and drag, etc. Numerical simulation methods. Computational fluid dynamics, CFD simulations, are instrumental in analyzing boundary layer dynamics. If you perform a CFD for the optimized compressor blades, its geometry and shape and angle of attack, we these simulate and we put it in the CFD. These simulations enable detailed examination of factors such as pressure distribution and flow velocity. Okay. సరే. These simulations enable detailed examination of factors such as pressure distribution and flow velocity to optimize compressor blade performance. If you perform a CFD for the designed compressor blades, we can get the examination on pressure distribution and flow velocity. It it's actually like an experimental for the design, experimental validation. Experimental techniques such as practical image velocimetry and wind tunnel testing and also CFD provide valuable data for validating boundary layer flow simulations. Combining experimental and numerical approaches enhances our understanding of compressor blade performance. Experimental validation is a must nowadays for the any kind of project or a design. Optimizing blade design. Integrating insights from boundary layer analysis allows for the optimization of compressor blade design factor. Factors such as blade curvature, surface roughness can be tailored for enhancing aerodynamic performance and minimize flow separation. Challenges and future research. Despite advancements, despite advancements, challenges such as transitional boundary layers and unsteady flow effects persist. Future research aims to address these challenges and further optimize compressor blade performance through enhanced boundary layer. Thank you.